So, in our course, so in this course, digital human modeling and simulation for virtual ergonomic evaluation. Now, today we are going to discuss our module 5, that is techniques and process of digital ergonomics evaluation using DHM. So, this is module 5. In module 5, this is our earlier slide where we discussed about we create digital human models using the digital human modeling software where this type of interfaces are there. We can put anthropometric data and accordingly we can create our digital human model as per our requirement. Similarly, we can either create this type of CAD model of the product or we can import from other CAD software to digital human modeling software. While this CAD model of the product and digital human model both are ready, then we give this human model to appropriate posture and using different types of reference points as we discussed in our earlier module. We position digital human models or mannequins in their respective workstation. Then we go for different types of ergonomic evaluation. So, this is the basic steps. Now, while we are going for various ergonomics or human factor issues for evaluating with digital human modeling software in virtual environment, then how we can do that one? So, for that purpose, obviously we need to know the human factor issues, contextual knowledge of those evaluating variables we must know, and why we will know those variables for evaluation and their requirement, then we will go for virtual ergonomic evaluation using DHM. So, first we are going to discuss about clearance and interference. So, clearance dimensions. There are different types of clearance dimensions like head clearance, thigh clearance, leg room. Head clearance, a minimum 5 cm head clearance for jolt in a vehicle is recommended. So, while we are talking about automotive design, then in that vehicle, driver, passengers, while seated or they are in like a bus or any other vehicle, while people are in standing, bus, train, while people are in standing condition, then how much space is there above the head to the roof, that is the clearance dimension. So, that clearance dimension should be minimum 5 cm for automobile, because during jerking or during jolt or during motion either driver's head or passenger's head may hit with the vehicle roof. So, for that purpose minimum 5 cm is required. Moreover, it is better if we can provide additional clearance space. In vehicular workstation, available head clearance must be sufficient for wearing and removing helmet in seated posture in the seat. Here two examples given. So, if this is a door, while we are evaluating that door in terms of its height, that whether this height of the door is sufficient, how we can evaluate that? We can visually inspect the dimension, positioning one, digital intended user population. We can create this type of 95th percentile digital human model using that anthropometric data of our intended population who are going to use this facility. So, if this is a 95th percentile or 99th percentile mannequin, if we position that in front of the door, then we can visually check whether that head clearance is sufficient or not. If we find that it is sufficient, then we can go ahead with that design. Otherwise, we need to increase that door height. Similarly, we can, while we are designing this type of workstation where people are doing some activities, then overhead storage racks and its position, you have to check whether that may touch with the head of larger mannequin with 95th percentile or 99th percentile mannequin, we can position and we can check that whether the clearance space is sufficient or not. So in this case, we can find that in this particular workstation, that overhead storage racks are not positioned properly because it may collide with the head. It may be acceptable for shorter mannequin, 5th percentile or 50th%, but it may not be acceptable for 90th percentile. So while this type of clearance dimension we want to evaluate, then we have to evaluate with larger body dimension. Then if we discuss about leg room, so leg room is the space in front of those people who are seated, whether that they can extend their leg comfortably or not. So Pheasant 1986 calculated the total horizontal distance between buttock and toes to derive leg room. So they have given this equation. So while some person is seated on that seat, while the space in front of him is sufficient so that they can extend the leg. So using this equation where all the variables are defined, so from that we can calculate the leg space. So this is theoretical portion, but apart from that, while we are evaluating our facility using mannequin, then we can position that mannequins of defined percentiles, a shorter mannequin with smaller dimension, mannequin with average dimension, mannequin with larger dimension. Then we can manipulate the leg extension and we can check whether the available space is sufficient for leg extension or normal leg movement or not. That we can check. So in this way, visually we can inspect the leg room. Similarly, whether there is sufficient thigh clearance or not below the tabletop or the surface, that we can also visually check after positioning that mannequin. So in this type of evaluation, generally we evaluate with larger body dimension, because if larger person or larger individual is accommodated, then obviously shorter individual will be accommodated. Shorter individual with smaller body dimension, they will be accommodated. The next is lateral clearance. So while people are seated side by side, the space in between two persons is sufficient or not, or while they are walking side by side, that available space is sufficient for movement of two person or more persons as per the requirement, that we can evaluate. While we want to evaluate this type of clearance dimension, lateral clearance, using digital human model, then we must know the basic theoretical background. So conventionally, 95th percentile bideltoid breadth of the population with an additional allowance of 10% on each side can be considered adequate for lateral clearance during normal sitting side by side. Chakraborty and Nag 1996, they mention lateral clearance space for a single person, that is maximum body breadth at elbow level with additional clearance for clothing about 65 centimeter. So 90 centimeter to 100 centimeter clearance as the maximum abduction of the upper arm with bent elbow at the shoulder level for adequate lateral movement. So this type of informations are available, and based on that information we can evaluate that while we are positioning these chairs or any other facilities, that the space in between two sitting position is sufficient or not, so that the individual who are seated there, they can sit comfortably and they can use the horizontal space as per their requirement. Similarly, if we think about the width of the door, while we are evaluating the width of the door, then we can put one 95th percentile mannequin whose shoulder breadth or bideltoid breadth is the maximum. We can put 95th or 99th percentile mannequin, and we can check whether that person can easily come in and out. So from the visual inspection also we can understand that door dimension is correct or wrong. Thompson et al. 1963 mentioned minimum 61 centimeter width and minimum 203 centimeter height for designing walkway for easy passage for a very broad shoulder and tall person. So this much width and this much height should be provided for walkway. Minimum clearance for easel and corridors design have been made by various researchers. So Thompson et al., Woodson et al., these are the references. From these references, we will find minimum clearance dimension for corridors design will be available. So based on those references, we can initially design our product or that facility. After that, through visual inspection, by positioning digital human model, we can check that whether our facility design is proper or not. So if we take this example, this is a conference room. In conference room, these are the stairs and this is the arrangement of seats. So while chairs are arranged in that manner, then the space, the middle space is actually provided for two persons side by side walking. So if we want to evaluate this one, then what we need to do? We need to put two digital human models or mannequins of larger body dimensions, say 95th percentile or 95th percentile. Then we can check that while we can simulate their movement and we can check whether two persons are going side by side, whether their body parts are colliding with each other or not. Similarly, in other places, we can say this is example from air cockpit. So while pilot is manipulating that joystick, moving sidewise or forward backward, that time whether the joystick or his hand is touching with the thigh. So that can also we can visually inspect. And also with collision detection techniques, what we discussed in our earlier module, with collision detection technique also we can identify whether there is any collision. So in this way, different types of clearance dimension we can study. Head clearance, leg room, thigh clearance, lateral clearance. So this can be studied with digital human modeling software. Here is another reference from Das and Sengupta 1996. They have given this table, anthropometric measurement for female for lateral clearance. What should be the anthropometric measurement for lateral clearance for female population? So 5th percentile, 50th percentile, 95th percentile, for 3 percentile people, they have given this type of calculated values. Clearance at waist level, clearance at elbow level, what is required. So these data we can refer for our design purpose. So as we mentioned, similarly, if we look at this particular workstation, these type of tables are there or arrangements are there. So the space in between these two arrangements, whether is it sufficient for two large person with larger body dimension can go side by side, that we can check. So in this way, we can explain this thing with numerous examples using digital human model, that how digital human model can be used for clearance dimension evaluation. Next, we are moving to reach analysis. Apart from clearance analysis, digital human modeling software are very useful for reach analysis. So here is also contextual knowledge of reach evaluation is important. For that purpose, we are discussing about this image. So normal and maximal horizontal work areas proposed by Barnes and superimposed with the horizontal work areas proposed by Squires, adapted from this source. So here, while some individual is sitting on in front of a table, or this is that working area, then these are the spaces. This is the sweeping of the left hand, this is the sweeping zone of the right hand. So this area overall that person can access, but combining these two area, ultimately the working area has been defined by this one, by Squires. then recommended work surface of 35 centimeter to 45 centimeter for work area and 50 centimeter to 65 centimeter for grasp area based on 5th percentile hand reach of men and women. So that this type of information is available, that how much should be the recommended limit for working area, so that person can do their activities comfortably. So you can go through these sources and you can read more to understand about ridge zones. Now there are different types of ridge. We can, from that person on that horizontal work surface, we can categorize like this way: 1, 2, 3, 4. These are the different ridge zones based on the level. The first level, nearby the body, that area is difficult to use. So first horizontal ridge zone radius 10 centimeter to 32 centimeter from the center edge. Center radius from the center edge, that is center radius point. So from this point 10 centimeter to 32 centimeter, that is first horizontal ridge zone. And just in front of that person, whatever is that area below that 10 centimeter area, that is actually difficult to reach, that is actually idle zone. After that, this area is called first ridge zone. There is second ridge zone from within a radius of 32 to 62 centimeter from the CRP, that is the center radius point. From center radius point 32 to 62, within this zone, that is called second ridge zone. Similarly, they have defined the third ridge zone. So this information is available from PLAT 2003. Different areas of horizontal ridge zones. One here, 1, 2, 3, 4 stands for first, second and third horizontal ridge zones. So in this way, you can see that where in different ridge zone area, where you should position of what items, so which are more frequently used by that individual, those to be kept nearby, and gradually other items which are not frequently used, that can be kept in zone 4 or zone 3. So in fourth, similar in this way, first ridge zone, second ridge zone, and in third, then fourth horizontal ridge zone, full body movement is needed to reach the tools or equipment. Apart from this, even extended arm reach with bending forward, that is also possible. Here this image is taken from Chengalur et al. 2004. So in this reference, what we can see, that this is the lines actually defining the ridge zone for from center line 38 centimeter right from the center line, and this dotted line is 52 centimeter right from the center line. So while person is seated and accessing that vertical area, so in different direction in the center line, how much area they can access, while it is moving to side, left or right side, then what's the area of access. So and the values are given in both centimeter and inches. So this type of data are available, and those data we can use for our design purpose. And this is taken from Bichet 2012 maximum reach study. So for reach study, this type of box we can develop, and there we can study that while driver or any other person whose reach we want to evaluate, how much they can reach. So with that extended arm reach, or here this is taken from automotive for evaluating that automatic driving posture and their reach. So in that type of bar, what is the reach area. So that this is actually a setup. With this setup, we can evaluate the forward arm reach, sidewise arm reach, or vertical arm reach. Similar to sitting, we can also go for standing reach evaluation. So in standing, so just in front of that person at the center line, this is a vertical reach zone line. Similarly, a vertical reach line. Similarly, if it is moving left side or right side, these are the defined. It is defined with this type of dotted line. This one is 46 centimeter to the right from the center line. This dotted line is to or 61 centimeter right to the center line. So first one, this is defined for the just in front of that person, how much area he can reach in vertical plane. Similarly, these are while it is moving from midline to sidewise, then how much is the reach, that is defined with this picture. Similarly, Flag 2003, they have also mentioned in some other way that these are the defined reach zones, region 1, region 2, region 3. So accordingly, we can position our intended equipments or work accessories in different regions as per our use. Now this reach can be evaluated using detailed modeling software. While we are discussing about reach, then one is normal reach, while someone is seated or standing, and normally while shoulder is straight or sitting with erect posture, how much area he can or she can access, we can evaluate. Apart from that, while body movement is allowed, means they can move or they can bend forward or backward, then obviously the reach area is more. Not only that, while the person is standing or leaning one step forward or backward, then again the overall reach area or reach envelope increases. So this type of normal reach zone, extended reach zone, we can evaluate. Not only this normal and extended reach zone, we can also evaluate comfort range of reach. In comfortably, in which area person can do their activities comfortably, where extended arm reach or arm extension or leg extension or any other body part extension is not required. So accordingly, this digital human being software is also helpful for defining those comfortable reach zone. Apart from normal reach zone, extended reach zone, we can also evaluate comfort reach zone using this type of software. So here we are discussing about example from CATIA software. In CATIA software, how we can create reach envelope for our evaluation. So there is this type of tools that is called computer reach envelope. So if you click on that one, then it will show this type of window. Range of motion, current, specific, physiological, maximal, ideal. So you can select. So if we can select ideal, then side, there are also options both side, left, right. So we are going for right. Then for which body segment you have to identify, you have to define that body segment here. So middle finger or index finger, which finger or fingertip or any other portion of the body you can mention here. Then it will create this type of reach envelope. This reach envelope actually shows the area, overall access area by that person. Similarly, in other software, here we are describing using JAX software. In JAX software, there is also this type of different types of reach zone we can create. Joint angle driven from shoulder, mean that person joint angle, hand is moving from the shoulder. So upper body or trunk is fixed, hand is moving from the shoulder joint. And how much reach, accordingly you can calculate. You can create the reach envelope. Joint angle driven from waist, axial rotation. So not only from the shoulder, the actually body is moving from the waist joint. So it will create a more bigger reach zone, because body hand is moving starting from that waist joint and axial rotation is also provided. So reach zone will be more. Similarly, we can go for comfort solid creation, constant driven. So constant driven, if we talk about this tool, so how we can put any particular constant for a particular body joint. If we mention that we want to evaluate the reach for fingertip, but not from the shoulder joint, from elbow joint. So first we have to define that our constant is that hand will move only from elbow joint. So only movement from the elbow joint will happen, not from the shoulder joint. So in that way, with constant driven also we can create reach envelope. So here it is an example of, you can also set the resolution, all this. So this is the for finger, right, human right finger, for that particular finger it is creating that reach zone. And again in that software there are different types of visual different, we can display. It is in wireframe mode, we can visual it in shaded mode, we can represent it in transparent mode. So there are different modes of representation also. So in this particular example, we can see while this particular individual, mannequin is seated on this seat and working on computer, then this is the zone where he can access. So during our workplace design, we have to position or frequently use items just in front of the human so that he can easily access. But other items he can keep little bit away, but within the reach envelope, so that all the items around him or her, they can access very easily. Here is again example from JAX software only. So here it is shown, if this is some products or equipment and if we want to put a barrier, so where should be the position of the barrier? So obviously we want that no one can touch the product. It may be hot, it may be some chemical, it may be some hazardous material. So we want to put a barrier so that people cannot access that one. Or if this is some display, so we are putting some boundary so that people cannot touch the display. So for that purpose, or exhibition, for that exhibition or display, so that they cannot touch. So obviously for 5th percentile or for people with shorter dimension, this is the position. So we can check it that this is the position of the boundary or barrier. But while this is 95th percentile, their reach is more. So accordingly, we have to decide, we have to ultimately we have to position that boundary or that barrier here, so that 95th percentile or 95th percentile mannequin cannot access that one. So if 95th percentile person cannot access that one, so obviously 50th and 95th percentile individual will not be able to access. So this type of restricted reach, for positioning this type of barrier, we can think about using detail modeling software. Similarly, with the detail modeling software, we can create this type of reach envelope. This is from side view and this is from top view. So from top view, we can understand this is the total reach area for that individual for right hand fingertip. So if this is a standing workstation, if we want to position his work accessories or work elements, so those should be kept within this reach envelope so that they can access those items for their work. So after discussing about various clearance dimension, reach, then we are moving to ergonomic evaluation of vision and view field using digital modeling software. So for evaluating vision or view field with digital modeling software, contextual knowledge is also important here. Student must know that how is our normal field of view, then how our eyes move, how our neck moves, because vision in general, how we visualize something, the light rays from that object, actually reflected light from that object coming to our eyes, eye or our sensory organ, through that light rays is passing and ultimately it is giving signal to our brain. So light rays, reflected light rays from the object entering through our eyes, falling on specific portion of the eye, that is called retina, and there is some chemical change, and based on that chemical change there is action potential generation, and that action potential is travels or proceed along the nerve, optical nerve, and it ultimately goes to brain, and it gives the impression of the image. Now, while we are looking at any object, how we look? We have eye movement, we have also neck movement. We can move our neck, we can move our eye. Eye can move independently. When our neck is fixed, only eye can move. When our eye is fixed, neck can move. At the same time, eye and neck both can move simultaneously. So, that is the basic understanding. For any object, while we are evaluating with digital modeling software, we can move the neck, but in many times, neck movement may not be required. Only with eye movement, that person can visualize. So, during evaluation, we have to understand whether that for the particular view field evaluation, whether neck movement is required or not. Because many things we can see only with eye movement. So, what's the range within which we can visualize any object only with eye movement, or where we actually require neck movement along with eye movement. So, for that purpose we have to understand this thing. So, generally for human being, with our right eye we can see 150 degree for right eye. Similarly, with left eye or in horizontal plane, we can see 150 degree. So, overlapping area of right hand and left eye, the right eye and left eye, that is coming to 120 degree. So, out of this 150 degree and this left 150 degree, the mid portion 120 degree is actually visualized by both the eyes. This area is called binocular field of view. In this field, we can visualize with both the eyes, but this area is visualized only with right eye, and this area is again visualized only with left eye. So, this is for horizontal direction. Now, in vertical direction, 50 to 55 degree up and 60 to 70 degree down, you can visualize. Henson 1993 mentioned binocular field of view is 60 degree vertically, out of that 25 degree up and 35 degree down. So, as per this reference, he mentioned normal binocular field of view 25 degree, this is the maximum movement, but generally we can move 25 degree up and 35 degree down for our normal world. Now, there are different types of view field: stationary field, eye field and head field. So, what we discussed here, this view field, actually this is obtained while our head is fixed, mean there is no head movement, only eye is moving. With eye movement we can visualize this portion. So, while our head, even not eye movement also, if we move our eye, then we can look at wider area. So, while chin is fixed or head is fixed, person is looking forward, at that time this is the field of view. Similarly, while head is fixed or neck is fixed and person is looking in front, then this is the area for vertical view. Now we are discussing around that particular focusing point. This thing will be much more clear if we draw this one. So, this is a line of sight. Well, one individual is fixing his or her eyes at a particular point, This is called line of sight. So this may be fixed here also. This may be the fixation point. So if he is looking at this point, he can fix his eyes at this point also. So this is line of fixation. Now we are going to discuss about the first one, stationary field, where peripheral viewing is sufficient. In stationary field, what we do, eye is stationary and head is also stationary. In eye field, as supplementary use of eye movement is required, and in head field, where head movement is also necessary. So generally what happens, where we are fixing our eyes, this is the line of fixation, around that this 15 degree up and 15 degree down this 30 degree angle. Around the line of fixation, this 30 degree view zone, 15 degree up and 15 degree down, this 30 degree area, whatever objects or whatever visuals are there, we can visualize very clearly without significant eye movement or head movement. This is known as stationary field or station field, where there is no eye movement as well as there is no head movement. So this is called stationary field. So generally stationary field is 30 degree. So this is stationary field, that is 30 degree. Then 30 to 80 degree, where there are eye movements, that is called eye field. Then if we extend this range from this 30 degree, this is a 30 degree view cone zone. After that, in this zone, beyond 30 degree but less than 80 degree. Within this zone, whatever is position, we can visualize with our eye movement. This is known as eye field. So first one, around the line of sight up to 30 degree, whatever is there, we can visualize clearly without significant eye movement and head movement. So head movement is not required, neck movement or eye movement is also not, head movement or neck movement not required, and eye movement is also not required within this zone. Eye is always moving. That is defined that for fixation, eye is always changes. But while eye is fixed at a particular point, around that up to 30 degree angle, whatever visuals are provided, that we can visualize without significant eye movement as well as neck movement. This area is known as station field. After that, from 30 degree to 80 degree, within this zone, whatever visuals are positioned, that we can visualize with our eye movement. With the effort of eye movement, we can visualize this zone. This zone is known as, so first one, this is stationary zone. Second zone is known as eye field. This is 30 degree to 80 degree. Beyond 80 degree, whatever visuals or objects are there, if we want to visualize, for that purpose, both our head movement as well as eye movement is required. So beyond this, if any object or visuals is at this area, beyond this zone, beyond 80 degree, then beyond 80 degree from line of sight. If eyes is fixed at a particular point, this is line of sight. Around that line of sight, beyond 80 degree, mean 40 degree up and 40 degree down, beyond 80 degree, if we want to visualize any object or items or any other visuals, then we need both our eye movement as well as neck movement. This zone is known as head field. So in head field, head movement is required, eye movement is required. In eye field, only eye movement is required, head or neck movement not required. And in stationary field, both head movement and eye movement both are not required. So this what we discussed, that is around the line of sight. Wherever we are fixing our eyes around that line of sight, this is the zone where we can visualize either with our eye movement or with head movement or with combination of both. Vankot and Kincaid 1972, they mention 15-degree angle most comfortable for viewing. While you are positioning any display, then 15-degree angle is comfortable, and we can extend it up to 30 degree. Frequently used for comfortable viewing where frequent changes of gaze between two equally important visual targets are critical. So while for our general purpose, we should try to keep our display in front of us, that is within 15-degree angle. But we can, if 2-3 displays are there or 2-3 visual targets are there which are equally important and we need to shift our gaze from one to another, then we can keep all those displays or all those visual targets within an angle of 30 degree. Now Grandkien 1988 mention distinct vision, viewing angle 1 degree foveal area, middle view viewing angle is 2 to 40 degree, and outer field viewing angle 40 to 70 degree. So he mentioned if we put around our line of sight within 1 degree viewing zone, whatever visuals are there, we can visualize very clearly. Distinct vision is possible. But from 2 degree to 40 degree within that zone, that is called middle field, where vision is little bit blurred, not that much distinct, like 1 degree foveal area. Then outer field, while that viewing angle is more than 40 degree to 70 degree, then we cannot, vision is not that much clear, where we can mainly identify moving objects. Field in that area, vision is not that much clear. Next information, this is taken from Xiao and Kaiserling 1991 and Woodson 92. So there they mention the 10 to 13 degree forward tilt angle while is generally observed for positioning upright vertical head position. So our head is always not erect. So while we are sitting or doing our activities, then generally our head is little bit forward tilted and that angle is 10 to 13 degree. This information is important for positioning the Eaton human model, because while we are initially creating the Eaton human model and positioning that human model in the respective workstation, generally head is in erect posture, neck angle is 0 degree. But for our evaluation purpose, as this is the normal human behavior, that human neck is with the vertical line, it is generally 10 to 13 degree forward tilted. So for our evaluation, so initially our neck posture should be given forward flexion of 10 to 13 degree. Then we should go for evaluation, because that is the normal situation. Then if that is the normal position of the head, then we will go for view field evaluation. Then whatever so far we discussed, that is the movement of mainly eye and view field. Apart from that, if we look at this one, that how much area, for our neck, with neck movement, what's the range of our neck movement? Horizontal left part of the figure and vertical plane right part of the figure of human head movement or neck movement. How much our neck can move? Because while you are discussing about vision, human vision, then already you have mentioned that human vision is also dependent on neck movement, because our eye can move, our neck can move, and that movement is independent and it may also move simultaneously. Head movement as well as eye movement may happen simultaneously. So here is the information regarding the range of head movement. So in horizontal plane, neck can move 45 degree sidewise, easy head movement, and maximum head movement is 60 degree sidewise. Similarly, up down vertically, easy head movement 30 degree up and down, and maximum head movement is 50 degree up and down. Now we are discussing about viewing distance. From this reference, Grandian 87, we find a common reading distance approximately 50 centimeter. So while individuals are reading some displays or any other reading material, that may be printed material also, so how should be the distance from eye to that particular object, viewing object? So common reading distance is 50 centimeter. Character height should be between 3 to 4.3 millimeter. Center for Disease Control USA 2000, they mention comfortable viewing distance for visual display unit work is 40 to 76 centimeter. So in general, we can find that 46 to 76 is also matching with this one. So for general purpose visual display work or visual display terminal or using on computer, laptop, for this type of purpose also we should position our laptop from eye point to 66 centimeter to 76 centimeter away for comfortable viewing. And for neck angle, we have already mentioned that monitor or display should be positioned below eye level. On the board, what we drawn, that was related to line of sight. Wherever we are looking at, around that line of sight, those are the angle. While we are discussing about station field, eye field, head field, those are around the line of sight. Here we are what we are discussing in this example, while you are positioning the monitor or any other display, then monitor should be positioned just in front of that individual, midline of the monitor and midline of the individual should match. Viewing distance would be 40 to 67 centimeter, 46 to 76 centimeter, and what should be the view cone? So monitor position should be such that it should come below the horizontal eye level within 15 degree, at the most 30 degree. So if we want to position our laptop monitor or computer monitor, then how should we position? So first we have to decide that horizontal line of sight. If this is the horizontal line of sight, below that so this is, assume this is 15 degree angle. So distance should be, the distance should be 46 to 76 centimeter, and the display should be positioned like this way. So if this is that monitor should be positioned within angle of 15 degree. This is the top line of the monitor screen, that should be below this one. So this is the horizontal eye level. Monitor should be positioned below that horizontal eye level within an angle of 15 degree, and it can go maximum 30 degree. If this is a big display or there are 2-3 display, then those displays should be positioned within this zone. So 2-3 displays are there, those displays should be positioned within this area, that is within 30 degree. So comfortable viewing angle is 15 degree below horizontal level, and we can go at the most 30 degree below the horizontal eye level for positioning our different types of displays, and viewing distance is 46 to 76 centimeter. So based on this information of our eye movement, neck movement and different types of view field, we can go for virtual ergonomic evaluation of view field or viewing by mannequins. So in different workstation we can position different percentile mannequin and we can check their vision. Here it is shown that within 30 degree view cone which display are visible and which display are not visible. So accordingly we can position the visual display unit. Now how we can use the software for this vision analysis purpose? If we take the example of CATIA software, in CATIA software this is that human model. So first we are selecting that human model, and for that human model we are going for vision analysis. So there is one tool called vision window. If you click on that vision window, then for that purpose what you are doing, first you are selecting that human, you are going for properties. It will open this type of window where this is the vision. Under vision you can change it binocular vision, monocular vision, vision of both eyes, vision of single eye. So we can select from this drop down list. Similarly we can also select the limits, that we can create that binocular field of view for 100 degree or horizontal ambicular, horizontal monocular 100 degree, horizontal ambicular 120 degree, vertical top, vertical bottom. So all these angle we can set, and based on that we can create our view field. Then we can display in different modes also. From vision then we can go for display. Here we can mention different types of vision, line of sight, field of view, view cone. So we will discuss one by one. So first one we are talking about this one, field of view. So if we select field of view and then go for analysis, then this type of field of view, binocular field of view will be generated. So while that individual is looking in front, looking there, at if this is that his view area, then actually how much area he can see, he can visualize his two hands. So that is coming in a separate window. So this is known as binocular view field. So similarly we can set monocular field of view also for left eye or right eye. If there is other objects also within this view field, those will also be identified here. So in this way, with this tool we can check the vision or view field for that mannequin. Next, if we look at this one, line of sight. So we can create also line of sight. So this type of line of sight is created. With this line of sight we can identify where that particular mannequin is looking at that particular point. So that point can also be denoted, can be identified with that line. This is called line of sight. We can, with that line of sight we can identify the fixation point. Similarly, we can go for view cone also. So this is view cone. We can create view cone. View cone, there are also different types of view cone also. From this drop down menu we can identify which type of view cone we want to create. We can change the angle, we can change the distance. For what distance? Say from this eye point we can up to 100 centimeter forward direction, and we can want to create an angle of 30 degree or 15 degree. Accordingly, we can define and we can create the view cone with these menus. Similarly, field of view, we can from display also we can select the field of view and we can create this type of field of view. Now, if we use JAX software, in JAX software also there is vision module. In that software, how we can evaluate vision? We can select that particular human, then display view cone. We can, for both the eyes, separate view cones are created. We can define the length and angle of that view cone, and accordingly we can generate this type of view cone. And whether our object or whether our display within that view cone or not, we can check it. Similarly, there are other tools known as eye view window. In eye view window, while that mannequin is looking at a display, then we can see how much area or what objects are coming within his field of view. So, for this is a separate window, this is another separate window. So, this is showing for left eye and this is for right eye. With left eye, that person can visualize this portion of the monitor, and with right eye, he can show this portion of the monitor. So, in front of him, whatever objects are there, while we are going for view field eye view window creation, then this type of windows are created where we can identify that which area or which objects that human mannequin is looking at. So, in this way, software to software, there are different types of tools and menus. With those tools and menus, we can go for different types of vision analysis. Now, here we are discussing, taking example from one cockpit evaluation. In that cockpit, whether the displays, different types of visual display position properly or not, we can either taking this example and we can evaluate that one. So, regarding vision evaluation, so we have positioned this type of digital human model. Say this is, we can mention 50th percentile or 50th percentile pilot. While the pilot is positioned, then we can create this type of 15 degree view cone. So, initially what we are doing, we are positioning, we are keeping that neck angle 10 to 13 degree. That is the normal human behavior, as we already mentioned in our earlier slide. Here, as per this reference, human neck is 10 to 13 degree in forward tilt. So, first we are giving this type of 10 to 15 degree forward tilted neck angle. Then we are creating eye view cone of 15 degree below horizontal eye level. Then we can find that this head of display is positioned correctly. So, pilot will be able to visualize that while his eye is at design eye point, then this pilot can see the head of display. This is side view, and this is one perspective view. Similarly, we can, if we create 30 degree view cone, then we find not only head of display, some other displays are also visible within the 30 degree angle. The same thing is also represented here. So, with creating view cone, we can check the position of the display and which displays are coming within that view cone. Now, if the driver move his neck, then the 30 degree view cone can be shifted like this way, left side or right direction. So, from this analysis, we can understand, although that while the driver is looking in front, straight ahead, then he can visualize this display. But with little bit neck movement, that neck angle also we can identify. With little bit neck movement, he can visualize all other display. So, what should be the neck movement range for visualize all the display? We can clearly identify using digital human modeling software. Similarly, here while there are side control panels, what should be the neck angle while that person is looking at the side control panel? That we can also identify, and we can calculate that neck angle also. So vision analysis module not only helping to identify the position of different displays within that view cone or view zone, and it is also allowing that the different to visualize different object or different viewing objects, what should be the angle of neck or movement of eyes, that also you can identify. Similarly, if bigger view cone is created 45 degree, then most of the displays are covered. So we can mention that in this particular case, with 45 degree view cone, most of the displays are visible. So here is one comparison starting from 15 degree, 30 degree and 45 degree. So while we are increasing the area of view cone starting from 15 to 45 degree, then we can gradually see which area of the displays are being covered. In most of these softwares, digital human link software, although this example is using JAX software, but in other software also there is this type of vision analysis tools. With that vision analysis tools, we can go for not only view cone, we can go for blind spot analysis. So blind spot, what is blind spot? We can study that one. The blind spot are some area in our view field where these are the zone where from if image is formed on our retina in a particular area on that retina, no image is actually visualized. That area is called blind spot. More elaborately, on our retina, the backside of our eyeball, on our retina, there is some area where actually visual information is not recorded because there is no visual receptor cell. Optical nerves, blood vessels are passing through that area. So inside our eyeball, on the retina, there is some area where nerve fibers and blood vessels are passing. At that particular area, there is no visual receptor cell. For that purpose, image is not formed there. So where that image is not formed, that area is actually corresponding to these two black cones. So if light rays or reflected light from objects goes through this direction and falling on our retina, so it will fall on that blind spot zone and image of that object will not be visualized. So in this area we cannot position any display. None of the display should be positioned in this zone. So pilot's basic purpose is he will look at the head up display. While he is fixing his eye on the head up display, then these are the two zones. From these zones, if light is come and falling on the retina, it is actually falling on the blind spot. And there is no visualization of image. For that purpose, during design of this cockpit, we should try to avoid keeping any display within this zone. So in JAX software, we can go for this type of blind spot evaluation. Similarly, we can evaluate reflection zone. Reflection zone means we can also mention as the mirror view. So through the mirror, so if it is a vehicle or if it is a cockpit, from that vehicle or cockpit, there are different types of rear view mirror, front view mirror. So from that rear view mirror or viewing mirror, we can visualize which area through that particular mirror will be visualized. So in this case, if these are the mirrors, that while pilot is looking at that mirror, which area of the back side will be visible with these three mirrors, 1, 2 and 3, these three mirrors, with these three mirrors, which area of the back side is visible to the pilot, that is actually reflected here. So due to this three mirror position, these are the area which is actually visible. So this external field of view through the mirror is actually depicted here. This is known as reflection zone or mirror zone. Like CATIA software also, in this case also we can evaluate eye view window. While pilot is looking at this display, then this is coming as a separate window. This is the zone which is visualized to the pilot. So this is coming as eye view window. So while he is looking at head-up display, so this top mirror and this portion is visualized. So that is shown in a separate window known as eye view window. Similarly, these softwares, not only JAK, in other softwares also, softwares have the capability to show obscuration zone. Due to the structure or this canopy bow, due to this canopy bow or this mirror, this is the area actually will be obscured. So while the pilot is looking, then due to existence of this canopy bow, this is the area where pilot cannot see. So that can also be evaluated with obscuration zone tool. Here is another example of obscuration zone. So while pilot is using this joystick and manipulating this joystick, during the navigation there is one display. Due to location of this joystick, that pilot cannot see this area. This is obscured zone. So this type of obscured area with this shaded zone is actually we can check using this type of obscuration zone tool. This obscuration zone tool is also available in this type of software. There is another example. Due to existence of this type of structure, beyond that structure, this zone actually not visible to this human. So we can create this type of obscuration zone using obscuration zone tool. So in most of these digital human modeling software, JAK, SAMI, Ramsys, then Delmia, we can go for different types of vision analysis tool. With this vision analysis tool, we can create view cone, eye view window, obscuration zone, reflection zone, and ultimately we can check that whatever facility, that may be driver, that may be vehicle, that may be air cockpit, that may be any other workstation, that or any other facility, that whether vision of that intended audience or intended targeted population is sufficient or not, whether they can do their routine activities related to vision related tasks. So that we can check with these various tools of those softwares. Next we are going to discuss about comfort and discomfort. Now in digital human modeling software, comfort is evaluated based on the body joint angle, and thus it is a quantitative analysis. But the observation is momentary in nature. For a particular posture, we can evaluate for that particular posture, for that particular moment, based on the body joint angle, we can identify whether that posture is comfortable or not. But what's the effect of prolonged duration of a particular posture? Well, there is a sustained postures or constant movement of human body. That scenario, in that case, how is the comfort? We cannot evaluate with this type of physical digital human model. The whole evaluation is based on only body joint angle. So effect of time is not coming into picture. Now, while we are discussing about comfort discomfort in digital modeling software, as it is dependent on body joint angle, so we are just referring our earlier module where it was mentioned that we need comfort database and range of motion data. So generally for different body joints, neck, shoulder, elbow, so in this for different body joints there is different degree of freedom, ventral flexion, dorsal flexion. So flexion, extension, adduction, abduction, different types of body parts movements are there, and we can also collect data. Based on that data we can calculate 5th percentile, 50th percentile, 95th percentile. So for a particular target population or intended population, we can collect for any particular body joints the range of motion data. After collecting the data, for both male and female, we can calculate different percentile values. As it is mentioned here, for neck joint, there are different degree of freedom, and in different degree of freedom, there are different percentile values. So that is calculated and tabulated. Now, this is data of range of motion, but throughout the whole range of motion, we cannot work comfortably. So, for example, if we consider the shoulder joint, and this is flexion and extension. So, in this case, this hand can move from this position to up to this position, but the entire range of motion is not comfortable. Out of this is the entire range of motion for this particular shoulder joint, when in this particular degree of freedom where there is flexion and extension. And out of this complete range of motion, based on the work activity, what type of work we are doing, whether seated work or standing work, or based on the nature of the work, we can define. So, for example, this is a standing work, probably the mid range of the shoulder movement, this range may be comfortable. So, not the entire range. Out of that entire range, a particular range of motion, that is defined as the comfort zone. So this comfort database, one is range of motion data. Out of that range of motion, a particular range which is defined as the comfort zone, that data is important. Why we have that data? Then we incorporate that data in digital human ruling software while we are developing that mannequin, and as per that body joint angle, we can analyze comfort. Now, different comfort databases are available for driver or occupant packaging. So, we find that these are the references for single joint postural analysis. So, these are the reference. From this reference, we can evaluate for a particular body joint, whether it is shoulder joint or elbow joint or wrist joint, whether that joint is within comfort range or not. But there is also multiple joint or overall body posture analysis from Christ 1994. So, based on various different joints in our body, we can calculate whether that posture is comfortable or not. So, this type of databases are available. We can use those databases for our comfort evaluation purpose. Now, if you see this recommended limit, design task, we need to design tasks to keep joints within the following limits. If we for general purpose work like performing routine or sustained work, in this case, neck angle should be within this range. Elbow angle should be 45 degree from vertical to the front or side for heavy extended work, 90 degree from the vertical to the front or side for occasional work. So, in this way, different types of comfort range of body joint angle is defined, and those based on those data we can evaluate comfort. Next, for driver or occupant, Porter 1998 defined different body joint angles, the range of comfort range of that body joint. For head flexion, he mentioned as it is starting from lower range is -10 and high is 26. So, if we consider that head flexion is within comfort zone, then it should be within -10 degree to 26 degree, and mode is 7 degree. Similarly, knee included left and right, it is starting from 99 degree low, and upper end is 138 degree, and mode is 121 degree. So, in this from different database, so we can use this type of body joint angle data for comfort analysis. This is the comfort range of motion for these body joints as proposed by Porter 1998. Similarly, for general purpose, for automotive industry, for driving posture, we can use this type of body joint angles. Now, this is important. The comfort database for driving posture is not applicable for while we are evaluating any task in standing posture. So we have to identify appropriate comfort database as per our requirement. So the database which is applicable for automobile or vehicle design, that database or driving comfort analysis, that driving comfort data is not applicable for evaluation of industrial workplace where standing work or bending work is involved. Different types of activities are going on. Out of those activities, various types of posture will be found. Those posture cannot be evaluated based on the comfort database defined for vehicle or automobile. So for different types of posture, so this is very important. Comfort range of motion for various body joint varies according to the posture, and for the particular posture, particular type of work, we have to identify the comfort database. If the comfort database is not available, then we have to develop the comfort database. Accordingly, we can evaluate the posture using digital human brain software. Without the comfort data, it is not possible. So here few examples are given. So while someone is doing some activity like this mannequin is tying shoelace, this type of forward bending posture is there, and leg only he is standing on one leg and another leg is on the at this place. Similarly, in this case it is a driving posture while driver is driving. So these postures are completely different. This is industrial workplace where workers are working, and that here the mannequin is in standing posture. So if I want to evaluate the comfort of various body joints for these three cases, the database required for comfort evaluation obviously different. So one database cannot be applicable for another, because for a particular type of work you have to define what's the comfort range. Now, if this comfort evaluation we explain with the example of various software. So first we are taking the example of CATIA software. While we are using CATIA software for body joint comfort evaluation for various body joints, then how we should proceed? So there is posture, you will find ergonomic design analysis. Under that we will find posture analysis, human posture analysis. So you have to click on that one, then this window will open. From that window you will find this type of tool. It is written edits the angular limitation and preferred angle. So you have that opportunity for a particular body joint. If we consider this elbow joint, the range of motion, complete range of motion or the total angular limits we can modify, because editing option is there. For that purpose, what we need to do, we need to first you have to select a particular body part, body segment. So assume we are selecting this lower arm and this particular elbow joint. So while we are selecting that elbow joint, then we will find this type of range of motion for this elbow joint. So starting from 0 degree and it is going up to 140 degree. Now this is the complete range of motion, which for this particular elbow joint it can move from 0 degree to 140 degree. This is not comfort range, this is the total range of motion. Now out of the total range of motion, now what we can do, we can change the limit. Now from this point we can, this limit, here we can edit this limit. So we can increase or decrease as per our comfort range database. Now change the how to change? So there is this type of angular limitation window. From that window you have selected the particular body parts and now activate manipulation. So you can manipulate. So lower limit you can set to 0 to 140 degree, it is already set. Now you can, as per your requirement, you can modify this one. If you have, for this particular body joint, if you have the data that what should be the range of motion for this particular body joint for your intended population, accordingly you can set the limit. So this is for range of motion. While the range of motion data is set, then you are going for defining the comfort zone. Out of the complete range of motion, now you are going to define the comfort zone. For that purpose, you have to right click on this one, you will find the add option. And also, for any particular joint, as per the degree of freedom, you have to find out that for which degree of freedom you are going for flexion, extension, or adduction, abduction, or rotation. For which degree of freedom you are going to modify the angular limit, and also you are going for evaluating the comfort. So for this flexion, extension, this is the complete range of motion. In that complete range of motion, now we are adding the comfort zone. So first we are dividing based on this reference data, Dreyfus Associate 2002. Based on that data, the whole comfort range, whole range of motion, we are dividing in 3 zones. So first zone we are dividing from 0 degree to 15 degree. This is not comfortable. So first zone we are defining as per this database, 0 to 15 degree is not comfort zone. So we are putting color red for that purpose, and we are defining the angle starting from 0 to 15 degree. Next we are adding one more. Next zone, which is from 5 degree to 100 degree, this range is the comfortable zone or comfort zone. So this is the second zone, then that is denoted with green. We are denoting with green color to indicate that this is the comfort zone. Then we are moving for third. Sorry. Now we are moving for third one. Again we are defining red color starting from 100 degree to 140 degree. Within this zone or within this range of motion, again work is not comfortable. So the first zone, this is not also comfortable zone, this one also not comfortable. The middle range of motion starting from 5 degree to 140 degree, within this range it is comfortable for working, standing working, or some other work activities. So in this way we have to define. But after defining, now the complete range of motion has been divided into 3 zones. Out of those 3 zones, this middle portion is defined as the comfort zone. Next, while after defining the comfort zone, body joint, individual body segment will not be highlighted with any particular color, although you have defined the color red and green. To highlight that particular body segment with a specific color, we have to go for next from that mannequin properties. While you are clicking on properties, this property window will open. While this property window is opening, from that window we are going for this tab coloring. Under that coloring tab, first we are clicking on activate, means coloring should be activated. Then what type of analysis? Postural score. Again you can from drop down menu you can change as per ruler score, Reva score, you can go for that one. Then show color for which segment? For all the body segments. So elements of color, segments and surface both show for elements and surface, and show all the colors, means show also red color and green color, and here show the color for both segments and surface. Now for which degree of freedom? Obviously we are now analyzing with flexion and extension. This flexion and extension we are now analyzing. Now after activating this, while it is activated for these segments, then if we go for, if we click on OK, then we will find this type of color. Now if we move this if we manipulate this particular body joint, means this elbow joint, if we move the hand up and down along this particular degree of freedom, then while hand is at this position, then hand color is this. Lower arm is denoted with red color. While the hand is moving in this middle portion, middle zone, that is comfort zone, now the color of the lower arm has been converted to green color. Now if we move the hand upward in this direction, then color of the hand, now you can see from this portion that now lower arm color has been changed to red color. So first we have to define the angular limit, then in that angular limit you have to define the comfort zone. while the comfort zone is defined, then you have to activate the coloring option. While coloring option is activated, after that, whenever you will manipulate that particular body joints as per defined degree of freedom, then accordingly color will be shown on the particular body segment. So this was whatever we discussed. This example was from CATIA software. But for other software, for example, next one, this is from JAX software. So in JAX software, how this comfort analysis is done based on body joint angle. So in this case, if we select that particular mannequin and go for comfort analysis, then it gives this type of color coding. For various body parts, it shows the angular value in degree, 15 degree, 8.2 degree, and if that is within comfort range, then it shows with as per this. In this particular case, analysis has been done as per the Dreyfus 3D method, and based on that method, for upper arm, if the flexion is 8.2, this is indicated with green color, means this is in comfort zone. But the left arm is not in comfort zone because that is indicated with yellow color. So with color coding option, we can understand that which body parts is within comfort range of motion and which body parts out of that range. So that is actually I was shown from this table, and you can find out that difference in color in different body segments. Next, few other example. So in these examples, already comfort joints or comfort range of motion for different body joints have already been defined. After defining comfort range of motion for different body joints, we are going for evaluating various types of products and workstation. During that time, so in this case, while that mannequin is using grass cutter or handling grass cutter machine, during grass cutter machine, what is happening? These few body parts are indicated with red color. Means those body parts, this clavicular portion and lower back, those portion is indicated with red color. Means these body segments are beyond the defined comfort zone or comfort range. Similarly, in other example, here while this we are evaluating Paddy Thresher in virtual environment, and we have defined the body joint angles comfort as per the comfort database, then we can find this 5th percentile female, it is showing with these body parts in yellow color, but these body parts in green color. I mean this is in comfort range, but these body parts are beyond comfort range because they need to bend forward. But in case of 95th percentile male, the situation is worst because these body parts again indicated with the next color coding, that is orange. So while there is no discomfort, then blue color, while there is discomfort, then it is indicated first with yellow, then if you can define with other colors also. If it is beyond, if it is severe discomfort, then it will be shown with some other color, red or orange. So in this way, with color coding option, we can evaluate our particular product or workstation while that mannequin is while you are making a simulation where mannequin is performing some task. During that task at various body segments, using comfort data, we can evaluate comfort using color coding. Similarly, in this example, while this person is using this podium, as this is a 5th percentile mannequin and standing on the ground, this is height of the surface of the podium is actually not comfortable for this person. His lower arm is actually indicated with red color. But if we increase the height, if we use this type of say some extended structure, if we use this structure, then he can stand on that structure so that they can easily, now his hand posture has been changed. Initially hand posture was like this, like this type of acute curvature was there, but now while that 5th percentile mannequin is kept on this type of platform, then what is happening? Now that person can stand on this one, his height has been now, vertical position has been changed, and now hand elbow joint angle has also been changed. Now color is indicated with green. So in this way, using color coding, we can evaluate our product or facility. Now after discussing about comfort evaluation based on comfort database for various body joints, and also by indicating color coding, using color coding, now we are moving towards spinal load or lower back analysis. So this is also another feature for most of the digital human being software, where we can evaluate low back analysis or spinal load analysis. In our earlier module, we discussed that this is our vertebral column. In vertebral column, different regions are there. So we mentioned like thoracic, cervical portion, then thoracic portion, then lumbar portion, sacral portion. So different regions or zones we define. So this particular portion is known as lumbar zone. So there are total 5 bones in lumbar segment. So out of those 5 lumbar vertebrae, between L4 and L5, so also we have already discussed that these vertebrae, through these vertebrae our spinal cord is passing by, and in between two vertebrae we find this type of cartilaginous padding material, which is known as intervertebral disc. So in between two vertebra we find this type of intervertebral disc. So this is one vertebra, this is another vertebra. So in this way all the vertebrae are arranged, and this between these two vertebra we are finding this type of cartilaginous material, that is known as intervertebral disc. During our movement for forward bending or lateral bending or leaning, that time this intervertebral disc get compressed due to this structure. Sometimes there is compressive force on this intervertebral disc, sometimes there is shearing force. So we discussed in our earlier module. So now with digital human modeling software we can evaluate how much is the compressive force or shearing force in intervertebral disc while some particular task is being performed by the mannequin and particular posture is adopted. So generally that analysis is done at the level of L4, L5, mean lumbar segment 4 and 5. In between these two lumbar segment, the intervertebral disc, at that region we measure the intervertebral disc pressure. So disc pressure is, as we mentioned, two types: compressive forces are there and also shearing force is also there. The compressive force generated in L4, L5 lumbar spine due to mass of the body or load acting on hand or any other body parts have an allowable limit of 3433 Newton, and this is the allowable limit, mean safe limit. If the compressive force generated at L4, L5 lumbar spine, if it is less than 3433 Newton, then it is within safe limit. But and the maximum permissible limit is 6376 Newton, means 6376 Newton. That is the maximal permissible limit. It is recommended by NIOSH. So this is the information regarding compressive force. So with digital human modeling software, we will measure that what's the compressive force at L4, L5 region, and if we find that force is less than 3433, then we will find there is no problem. That is within safe limit, but it obviously should not go beyond 6376 Newton. If it goes beyond that, then we need to modify the task so that posture will be changed and the person will be able to adopt defined posture where there is less spinal compression. So, this is compressive force. Next, another type of force is also acting there, that is shearing force. Compressive force means up down vertical pressure, and shearing force means forward backward or sidewise. Lateral shearing, that may be forward backward direction, also in lateral direction. So, a safe limit of 500 Newton with 1000 Newton as maximum permissible limit was suggested by University of Waterloo Ergonomic Research Group towards joint shear. So, if we follow this reference, then we will find for shearing force, its limit is, safe limit is 500 Newton and it can go maximum 1000 Newton. Now, how we can evaluate that? For evaluation purpose, we can use different software. Now, we are giving the example from JAX software. In JAX software, how we can do that one? So, there is one tool called lower back analysis. In lower back analysis tool, first we can give that particular working posture to that mannequin, and during that particular working posture, now we want to measure what's the L4, L5 spinal compression and shearing force. So, while we are giving that particular posture, at the same time, what we can do, we can also, there is another tab that is called load and weights. We can also define the loads, that some load, say for example 5 kg loads is acting on shoulder, or some load is on hand. So, those load we can also define, loads and weights. After defining those options are there, then we can go for analyzing. While we are activating this one, then it is giving this type of data. So, in this case, height is there, body weight it is already selected from the mannequin. Now, L4, L5 forces. So, one is compressive force, so that data is showing here. Then another is anterior posterior shear, that is also showing, and next one is lateral shear, that is almost negligible. If you find here, so as per the recommendation limit, whether this is within safe limit or not, that is also come at this particular place. So, here it is written the low back compression force, here it is calculated as regarding compression force, it is 1964 Newton is below Nair's back compression action limit, that is 3400 Newton. Thus, it is representing that there is nominal risk of low back injury. So, based on the compression force which is indicating a value of 1964 Newton, that is within the safe limit. Now, even we can plot graph for other variables also, like DHM moment distribution. So, this is polar histogram for that purpose. So, moment at various body joints, that is also shown here. Muscle tension for few selected muscle, it is also showing how much muscle tension may be while that person is adopting this type of posture. Then at various muscles, what may be the muscle tension, that is also represented in graphical form. And also it is showing, as it is shown in earlier case also, L4, L5 moments it is showing, and L4, L5 forces, compressive force or shearing force, that is also indicated. So, we can, from this analysis we can get this type of various analysis, moments, forces, muscle tension and distribution of moments. So, this example was from JAX software. In how using tools of JAX software, how we can evaluate lower back. Now, the same thing while we are evaluating low back or spinal compression or shearing force using other software like CATIA software. In CATIA software, this type of human model is there. How that analysis is done? So, first we have to go to start, then there we will find ergonomic design analysis. Under that we will go for human activity analysis. So, here you have to move for this particular tab, that is human activity analysis. While you will go for human activity analysis window, then this type of window will open where you will find biomechanics single action analysis. So you have to click on this tool, that is biomechanics single action analysis. While this tool is selected, then you have to give that particular mannequin a posture, that working posture, and during that working posture, now this window will open, that how is the forces at L4 L5 level, L4 L5 moment, L4 L5 compression force, then L4 L5 shearing force. So that value is indicated here. So you have to select that mannequin, you have to give specific posture. After that, while you are clicking on this particular tool, that is single biomechanics single action analysis, then we will get this type of scores for L4 L5 compression force, L4 L5 moment at L4 L5 segment, then compressive force as well as shearing force. So what we discussed still now, that is low back analysis using two different software. Now we are moving to next type of analysis, that is called postural load analysis. In different digital modeling software, we will find this type of tools: WAS, RULA, REBA. WAS, these are the posture analysis tool. Already these are well established ergonomic evaluation tool for evaluation of posture. Now all these tools may not be incorporated in all the software, software to software it varies. For example, in JAX software, WAS, RULA included, but in case of CATIA, then only there RULA is, WAS is not incorporated there. So in this way, software to software it varies. Now these tools are very important because with this ergonomic posture evaluation tool, we can determine injury risk, how to set priority to modification of that particular posture. I mean, first we need to modify the task, we have to set priority to modify the task and accordingly modifying the posture. Identifying whether need of training is there or not, then what if scenario. If we modify the workplace or task requirement or pattern of human body parts movement, then whether there is any change in the score of this postural evaluation tool. So first tool which we are going to evaluate, that is WAS, OWAS. The full form is Ovako Working Posture Analysis System. Ovako Working Posture Analysis System is a survey-based posture evaluation technique. It was developed in Finland and it was proposed by, or it was first designed by Karhu et al. 1977. WAS method orders the frequency and relative proportion of time each specific posture lasts and evaluates through a scale of 4 action categories. So in WAS techniques, there are 4 action categories. First we have to evaluate the posture. If we find what's the, as per this WAS technique, what's the score, and based on the score we can go for recommendation. There are 4 action categories. We have to, based on the score, we have to select which action category will be implemented in that particular posture. Now we must know about the, and we must have a basic understanding for WAS tool, then only we will be able to use that for our postural load evaluation using our digital human being software. So that if we understand the theoretical background, then we will find in WAS tool what is done. There are 4 body, these are the 3 body segments: back, arm and legs. Based on these 3 body posture or body orientation of these three body segments actually was evaluation is performed. So first these are the scores. Different types of back or trunk posture. If trunk is straight, then you have to put 1. If trunk is bent forward, for this particular case, if you take this particular posture, then you will find bent forward. Posture is bent forward. So out of this 1, 2, 3, 4 type of scores are there. Out of these 4 scores, we are identifying for this bent posture 2 is the score. Similarly, for arms, both arms are at elbow level, so different scores are there for different types of posture of arm. Out of that, in this case we are identifying it is applicable here is 1. So both arms are below shoulder level, so we are putting 1. Similarly, for legs there are total 7 postures may be there. So they have categorized the leg posture. Haru et al. They categorized in 7 postures of leg. Out of the 7 posture, we have to identify which one is applicable here. In this case, we find it is applicable 2. 2 means standing with both legs straight. So in this case, that person is standing on both legs. So score is 2. So back score is 2, arm score is 1, and leg score is 2. With that, we are adding another for load or use of force. So if there also it is defined as there may be 3 scores, 1, 2 and 3. Why? When it is 1, weight or force needed is 10 kg or less. While the force is 10 kg or less, then we are giving score of 1. While the weight or force weight or force needed exceed the amount of force which is required for that particular task. If it exceeds 10 kg but it is less than 20 kg, at that scenario score is 2. Then 3, weight or force needed exceed 20 kg. So these 3 types of scores are available. 1 while the weight or force is 10 kg or less, then value is 1. When it is 10 to 20 kg, then 2. While the weight or force requirement is 20 kg or more, then that is 3. So in this way, we can identify which one is applicable here. So here it is applicable 1. Then based on all these things, there is another chart. If we go to the next slide, then we will find from this chart. So already we know for back score it is 2. Then we are moving to arm score. From back score, if you see this one, back score is 2. Against that, arm score is 1. So first from this table we have to identify back score. This is the back score 2. Then arm score 1. Then leg score again 2. After that, so back score is 4 types. In this particular case, 2 is applicable. Then against 2, arm score may be 1, 2, 3. Here 1 is applicable. While arm score is 1, against that leg score may be total 7 types of leg score is available. Out of that, here it is applicable 2. While leg score is also identified, then we will ultimately find out the point, these 2, that is the posture, final score. So final score is coming 2 based on only on the posture, in posture of back, arm and leg. So score is coming 2. So action categories based on this final score is of 4 types. So in VAST technique, there are 4 action categories for the grand score. So 1, no corrective measures are required. Corrective, if the grand score is 2, then corrective measure is required in near future. If grand score is 3, then corrective measures is required as soon as possible. Otherwise, if grand score is 4, then corrective measures required immediately. So in this case, our grand score is, after putting all these things for back, arm and leg, then it is coming to final score 2. If final score is 2, then in this particular example, it is coming that corrective action or corrective measures is required in near future. So that is not that much problematic. Now this was just momentary observation. So after that, generally for this wash analysis, ruler away analysis, what we do, we have to record the posture. So in that working condition, we can go for photography or videography. That photography or videography can be recorded for the whole day or 8 hours work, or as per your requirement for a particular time duration. Out of that working duration, now we can calculate that out of the total working time, how much they have used this particular back. For back there are 4 type of posture. Out of the 100% working time, what's the ratio of using back in straight condition, what's the use of back for bent posture. So that is actually indicated from this table. Out of 100% working time, if back posture, if we find that back posture bent and forward, for that total 20% time, that particular individual during the 100% working time, 20% time he is actually spending while their back is bent forward. Accordingly, we can identify that back bent forward, this is the back posture, and for which duration they have calculated that. So bent forward with that particular posture, that person is say 20% of the working time he is spending with bent posture. So now his score is coming at 1. But if out of 100% working time, if for back posture, if it is bent forward for 80% of time, then it is coming to score 2. Similarly, for legs, if say 60% of time that person is on one knee bent, then that is score 5 for momentary observation. Leg score is 5, but one knee bent, and that person out of 100% working time, he is actually spending 60% time. So his score is coming to 5 bent, so it is coming at around 3. So in this way, this table is used to indicate which percentage of time that individual is spending with a particular posture of a particular body segment, that may be back or arm or leg, and based on that we can categorize action categories. So 4 action categories are there. Now this is the theoretical background. Now how we can evaluate with software. So just for recapitulation, so in wash method, what we did for wash method, this is, as we mentioned, this is a survey based method. For the survey based method, where people are working, then for a particular posture or for particular task, for a particular task, they have to, that observer or who is going for evaluation, they have to record the video. From that video, they have to identify the different frames. For one is momentary observation for a particular posture for that particular moment, where we can get this type of image or this type of photograph. Based on that, this particular posture, this is the score. From this way, from referring this table, we can calculate the grand score. Another is from videography. If we record the total working hours, that is the 100% working time, out of that 100% working time, which percentage of time is being spent with a particular body posture. If we can identify that, from that also we can go for suggesting various action categories. Now the same thing we can evaluate with digital human modeling software. While we are using digital human modeling software, then our task is much more easier, because while we are doing it manually, we have to record photography, then videograph, Then after that we have to identify various postures, we have to categorize them. Based on that category we have to put scores. Then we have to also study that load or force use. Then based on that we can calculate grand score and we can recommend specific action category. But in digital human modeling software it is very easy, where you can select a particular human with a particular working posture. This is obviously momentary observation, there is no effect of time. If we want to go for effect of time, then we have to define all those variables. So here this is was posture evaluation tool. While we are evaluating, this is from JAX software. In JAX software, if you select that human with a particular working posture and go for Ovako working posture analysis, then you will find this type of score. It is directly giving you the score, and below that score it is given which action category is applicable. So in this particular case, what score is coming 2,111. The work posture may have harmful effect because it is coming to 2. So harmful effect on musculoskeletal system. Musculoskeletal loading is not extreme with this posture. However, corrective measures are encouraged. Note that only downward force components are considered in the analysis, because that force has been from this load and weights, downward force has been defined. So this is showing here. Was scored for lower limbs was determined using loads and weights force distribution strategy. So in this particular posture we can define the load in different body parts or force exerted by particular body segments. After that, based on the posture and based on the load distribution, this software can calculate the postural score as per the VAS method, and based on that postural score it is giving the recommendation which action category should we follow. Similarly, in other softwares also posture evaluation tools are available, VAS tools are available, and we can evaluate Ovako working posture analysis we can perform. Then next is another posture evaluation method, that is called RULA. So first one was Ovako working posture analysis, the next one is RULA, rapid upper limb assessment. This is also a survey based method. So rapid upper limb assessment is a survey method developed for use in ergonomic investigations of workplaces where work related upper limb disorders are reported. So in that scenario RULA is used. RULA score sheet was developed by McAdam and Corlett 1993 to assess the exposure of people to postures, forces, to different types of postures, force and muscle use, which are known to contribute to upper limb disorder. So these factors, posture, force and muscle use or muscle activity, based on that actually RULA calculate the grand score. So in summary, RULA is a survey based method, assess postural score based on posture of neck, upper limb, loading. This method is good for sedentary and seated tasks because only upper limb is involved mainly in this evaluation, because in this case there is no separate score for lower limb analysis. So this is good for, this RULA analysis is good for sedentary work and seated work. Final risk, it provides final risk assessment score, combines arm, wrist risk with neck, trunk and leg. So these are the body segments. Based on the posture of this body segment it provides the score. Final score magnitude, it varies from 1 to 7. Overall injury risk due to musculoskeletal loading. For RULA method there are total 6 steps. First steps, like was also, here is observe the task. So we have to go for photography and videography. First we need to observe the task, how people are performing that particular task and what type of postures are they adopting. Next, second step is select postures for assessment, in which you identify out of those so many types of postures which are they are adopting during the posture, which are the key postures or which are most frequently adopted by them. So out of various types of postures for a particular task, you need to identify most frequently the postures which are most frequently being adopted and which are the awkward or worst posture which needed evaluation. Next, calculate the score of those posture, process the score and determine the final score. What's the final score? And accordingly suggest various action categories. Next, this is called ruler assessment sheet. In this, define body parts and how that body parts should be given defined score is explained. So first is part A, where arm wrist analysis performed. Then there is second part where step 2 so first part arm wrist analysis, second part neck, trunk and leg analysis. So from part A we are getting score from table A, from part B we are getting, there is another table, table B, we are getting some score. Then with that we are from next we are with that we are adding lookup posture score in table B, then step add muscle use score, then ultimately based on this we are from then we refer table C where from we can calculate the final score. So now if we go step by step. So first portion is arm and wrist analysis. So based on the posture of arm, these are the scores for upper arm. So based on various postures of upper arm, we can get the score. So all the scores are mentioned. That if upper arm position is like that, then you have to calculate 1. Then if upper arm posture is like this, then we have to add 4. So in this way, scores are defined. Similarly, score is also defined for lower arm. Similarly for wrist posture, it is defined. So from that, here we will find some scores. Say for example, we find some score for upper arm. These are the score 1, 2, 3, 4. In this way, total 6 scores are there for upper arm. Similarly for lower arm, these are the scores for lower arm. After that, we are putting the score for wrist. Then step 4. So this is the first 3 steps. Step 4, wrist twist. If there is wrist twist, then for that purpose also you have to add some score. Then step 5, look up posture score in table A. So next, after giving for all these body segments, upper arm, lower arm and wrist twist, based on this criteria, we are putting some score on this table A, and from that table we are calculating grand score for table A. So from table A, then add muscle use score for upper arm, the upper body is arm, lower arm. For that purpose, we have to go for add muscle use score. With this score, whatever score we are getting from here, with that we are adding muscle use score. Then add force use scores. For in this way, ultimately we are getting final score. Find the row in table C. So whatever score we are getting from table A, and for that this is the score. So total 3 tables are there. Table A, which is associated with arm wrist posture, then wrist twist, and then muscle use and force use. From this scores, we are ultimately referring this table A. From that table A, we are getting a specific grand score. With that grand score, while we are adding muscle score and force score, we are getting a score. Whatever score we are getting, that score is actually listed here, 1 to 8 plus. So if say for example, from calculating from table A, after that adding muscle score and force score, say we are getting 6 here. So that 6 we have to, this 6 value, next it will be referred to table C. So this 6 value is identified. So this is for this side. Similarly for neck, trunk and leg. So first portion we are evaluating the neck posture based on that score. What is the score? trunk posture based on the what will be the score. While these two are identified, trunk posture score and neck score, based on that from table B we are identifying some score. While that score is identified, with that score we are adding muscle use score and force or load handling score. After adding these two, we are getting a score. That score again will be referred to table C. So table C has two, this is horizontal axis, this is vertical axis. In horizontal axis, it is actually referring the score from this side, mean score from B, table B, with that muscle use score, with that force use score. So whatever grand score we got for the upper body portion, this neck, trunk, and with that after adding muscle use score and load or force handling, the whatever grand score we are getting, we are referring here this particular row of table C, where 1 to 8 plus score is mentioned for table C. Similarly, for arm, upper arm, lower arm, wrist, we are referring table A. Whatever score we are getting, with that score we are adding muscle use score, force use score. Whatever final score we are getting, that score again we are referring to this vertical, this column, where we are identifying, say for example it is score is 6 and here score is 5. So this 6 for group A and this group B. For group B, this is score is 5. So based on this 6 and 5, from this table we are identifying the final grand score. And that final grand score, there is different action categories. Based on that action categories, we have to decide. So there are, as we mentioned here, there are total 1 to 7 action categories. If we find that our what is our final grand score, if we find that our final grand score is 5, then as per that we have to go for recommendation. So recommendation final score, here it is mentioned 1 or 2, then it is acceptable. As in this particular example, as we are assuming that our final score is 5 from table C, then it is actually coming within this range, 5 or 6. So investigate further and change the posture soon. So we have to investigate further and we have to redesign the task, redesign the workplace in such a way so that this postural score can be reduced. Now this ruler can be evaluated with digital human doing software, where the mannequin or digital human model, while performing a particular task with a specific posture, in that posture if we select that human and you define various muscle use, already posture already identified by the software based on the body joints, so that is already identified. With that you have to add muscle use, force and load handling, and legs and feet, whether those are supported or not. So these type of options are there. This is for group A, as we have already discussed, group A. Similarly for group B, whether there is muscle use and load or force handling, that you have to define. So body group A, arm and wrist, for that these are the three components: muscle use, force and leg. For group B, there is muscle use and force and loads, because overall posture is already been identified. If we go back to this one, so for group A, these are the things where arm, wrist and legs are involved, with that muscle and force is involved. Similarly in group B, neck, trunk, legs are there, with that muscle and force has been added, and finally we get the grand score. In software, already posture is identified. Additionally we have to add this thing for group A, that is muscle use, force use and leg and feet condition. And for group B, again we have to define the muscle use and force. Based on this data, it will ultimately give this type of grand score. So here, based on the input parameters, it is giving grand score of 6, and accordingly action categories investigate and changes are required soon. So based on grand score 6, it is giving the recommendation. So in digital human well-being software, here we are giving the example from JAX software. So for 2 segments of body parts, we are defining the body joints, muscle use, load use, and posture has already been identified by the software. Based on that, it is giving the score, and that's based on that score, it is giving the recommendation. So it is very much easy to use. Similarly, in CATIA software, there also we can evaluate a ruler. There, if we want to go for ruler evaluation, then we will find this tool. This is called give post. This tool is name is ruler. For that purpose, what we need to do, we have to give particular posture to that mannequin for which we want to evaluate that ruler score. Then this ruler analysis window will open, where you have to specify, because in ruler analysis we have to evaluate our left side of the body or right side of the body separately. Both cannot be calculated together. So first you can calculate, because left hand or left leg, that posture of left hand or left leg may be defined for right side of the body. Means posture of left hand may be different from posture of right hand. Similarly, posture of left leg may be different from right leg. So that's why left side of the body is evaluated separately from right side of the body. So in ruler analysis, so if we go for left side analysis first, so few body parts which are common, which is say head, trunk, for that there is no left right, but for other hand and leg we need to go for left and right side of evaluation. So side, it is indicated here left, we are evaluating left side. Then type of posture, whether static, intermittent or repeated, that we can identify, we can mention. Then repeat frequency, how frequently that particular body parts are moving, we can also mention if the task is being performed, that also we can give. Then condition of arm, unsupported or not, whether it is body is balanced or not. So based on all these criteria, and also whether they are handling any load, that we can give. While all these things are defined, based on that it is giving the final score. Not only final score, it is also for individual body segments, what's the score, that is also being provided. Based on individual body part score, it is giving the final grand score, and that score is 3, and it is indicated with yellow color. It means investigation further required. So in this way, with this digital human modeling software, we just discussed with the example of from JAX software and CATIA software, but most of the digital human modeling software has the capability of evaluating this type of postural load using various postural evaluation tools like ruler, REBA, OWASP. Now we are moving to key learnings from this module 5. In module 5, we discussed about, from the very beginning, if we recapitulate, we will find we have discussed about study of clearance, dimension and clearance and interference. So here we discussed about head clearance, leg clearance, thigh clearance, lateral clearance, and we explained how we studied the theoretical background. At the same time, we demonstrated with JAX or CATIA software that how software tool can be used for evaluation this clearance and interference. Here we also discussed about collision detection techniques. Then we moved to reach analysis. So after studying various theoretical aspects, then we mentioned how reach is evaluated with digital human modeling software, where we discussed about extended reach, normal reach, at the same time comfort reach, and reach constraint driven reach. So various types of reach can be evaluated with different types of tools available in the software. So that reach analysis also being performed and shown. Next we discussed about field of vision or view field. In field of vision or view field, we discussed about eye view angle, view cone, then eye view window, reflection zone, obscuration zone. So different types of tools which are available in digital modeling software, and with those tools how we can evaluate vision or view field, that has been discussed. Next we discussed comfort and discomfort. So comfort and discomfort analysis in digital human living software is performed mainly based on the body joint angles, and based on the comfort range of that particular body joint we can define that whether that particular body joint is within comfort range or not. And if it is, in this many of these software there is color coding option, and color, the particular body segment is highlighted with a specific color to indicate whether that is within comfort range or not. Then we discussed about spinal load analysis and low back analysis. Here we mainly discussed about spinal compression force at L4 L5 segment and also shearing force at L4 L5 vertebral segment. So how much intervertebral disc pressure is there, that we discussed here. Then we discussed about postural load analysis using various ergonomic evaluation tool for posture like Rula, WAS, and also we demonstrated with software use. So this is the overall learning from module 5. Now these are the references. These references has been cited in different slides. So students can go through these references, they can explore to get more information regarding those tools or different information which has been provided in various slides. Thank you.